In this video, I will talk about the curl and the divergence of the magnetic field. And I will start with the easy one. The divergence of B is always equal to 0. Now, this is the differential form of Gauss's law for magnetism. And if we want to write Gauss's law for magnetism in the integral form, then that would look like the closed surface integral of B dot dA is always equal to 0. Now, if you remember, for electricity, Gauss's law for the electric field was dependent on the charge density or on the charge enclosed. It was the closed surface integral of E dot dA is equal to the charge enclosed over epsilon naught. Now, if you think about it, for electric field, the charge enclosed was referring to the monopole term, if you want, from the expansion into the monopole, dipole, quadrupole, and so on, to those terms. The charge enclosed for Gauss's law in electricity was about monopoles. Now, we know, at least until now, the best experimental evidence that we have says that there are no magnetic charges, there are no magnetic monopoles, I should say better. And this is the reason why Gauss's law for magnetism always has a 0 on the right side. Okay, Gauss's law for the electric field includes electric charges. Since there are no magnetic monopoles, Gauss's law always has 0 for the right side. Alright, so this is Gauss's law for magnetism. Now, this is Ampere's law. And in the differential form, this says that the curl of the magnetic field is equal to mu naught, the constant, times the current density. But you can also write the same expression into an integral form. That is the closed path integral of B dot dl is equal to the constant mu naught times the enclosed conventional current. Now, I want to talk about a little bit how you can use Ampere's law. Now, I forgot to mention this. Regarding Gauss's law, there are not really many ways that you can use it. Okay, since the right side is always 0, the only way that I can see using Gauss's law, if you're given a pattern, a magnetic field, a magnetic vector field, you may be asked to determine whether that magnetic field pattern is consistent with Gauss's law or not. And the way to do that, if you calculate the divergence of B and you find the divergence of B to be not 0, then that magnetic field pattern is not consistent with Gauss's law. Okay, that's the only way that I can see some use for Gauss's law for magnetism, just to be able to reject physically not possible patterns for magnetic field. Now, for Ampere's law, actually Ampere's law is useful, and the ways that you can use it, if you're given B, if you know what the magnetic field is, then you can calculate the curl of B and then obtain the current density. Now, a different way to use it, actually this one is somewhat similar. If you have B again and you calculate a closed path integral of B dot dl, you can find the current enclosed. Now remember, of course, the current density and the conventional current are related. That's why that's how these two can be used in the same way. Now there is one more way that you can use Ampere's law. Okay, so far I told you if you know B you can find I, but if your problem has symmetry and you can take the magnitude of B out of the integral as a constant, then you can solve for B, for the magnitude of B from Ampere's law, if you know the current. So this is another use for Ampere's law, and this use is similar to what we do for electricity using Gauss's law. Okay. I want to remind you, we had E dot dA is equal to the charge enclosed over epsilon naught. When we had symmetry, we were able to take E out of the integral and we were able to solve for E if you knew what the charge enclosed was. And this is similar here for Ampere's law in magnetism. Due to symmetry, sometimes you can take B out and you can solve for it. All right, so these are the two ways that you can use Ampere's law. Now, I want to mention something important about the integral form of Gauss's law. Okay, you do need to remember that this is a closed path integral. Now, the way that I would like to see applications of Ampere's law in problems, okay, we have the first thing that we will do in problems, I want to see what is the vector B, and then I want to know what is the vector dl. Okay, whatever coordinate system needs to be used for the problem, we need to specify the coordinate system, we need to write the vector B, we need to write the vector dl. Once you have those two, then you can find their dot product, and that combined with the definition for the path, okay, you need to define the closed path. It has to be a closed path. Then you can find the right side, or maybe solve for B if you know the current enclosed and so on. But make sure you define you decide on a coordinate system. Make sure you write the vectors B, the vectors dl, find the dot product, move on, and then with the definition of the closed path, then you can move on and finish the problem with all these steps. There is something though that is important to remember. We have a current on the right side, and we have a magnetic field and a closed path integral. Now, you will need to use, whenever you apply Ampere's law in the integral form, you will have to use the right hand rule to specify what is a positive current and also with the right hand rule you will specify the direction of integration for the closed path. And I will show you some examples what I mean with that. Let's say that I choose to integrate clockwise. This is my closed path, it's a circle. So my closed path is a circle and I'm integrating in the clockwise direction. Now if you take your right hand and you curl your 4 fingers in the clockwise direction, you will find that your thumb shows you a direction that is into the board. This means that a positive current, okay, for you, in this case, a positive current needs to be moving into the page. So once you specify, so there are a number of things you can do. You can specify what's the direction of the positive current first, and then you can use the right hand rule to see which way you will need to do the integration. On the other hand, you can also choose how you will do the integration of the closed path integral, and then use the right hand rule to find out what is the direction of the positive current. Okay, but you cannot do both. You cannot specify both the direction of the positive current and the direction of integration. You have to use the right hand rule. Now, one more example. We're here and I decide to integrate in the counterclockwise direction. Then if I curl my fingers in the counterclockwise direction, I see that my thumb points out of the page, and this is the direction of a positive current. A positive current would flow out of the page for this direction of integration. Okay, the way that you apply Ampere's law needs to be consistent with the right hand rule, and you have to be careful about that.